with something called a circuit. You have a battery, some wires, and a device that uses electricity such as a light bulb. Electricity flows through the circuit. But as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow the other way. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. Magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on, it's always working, you can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bolt which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now in reality, connecting these wires would prevent the bolt from spinning freely, but what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor. But we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with two brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's two brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now so far we've only used one loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position, with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these two commutator segments, which turns on this electromagnet, which causes it to start spinning. Once we get to here, the brushes switch contact to the next pair of commutator segments, which means this loop turns off and the next loop turns on. Now this electromagnet wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt, and it's also true when each of our armature loops are made of many wires. The motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the two permanent magnets on the side. These fit inside the edges of the motor case. The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these two pieces back and forth.